Okay, this is a rolling motion problem without slipping, where a hoop and a cylinder with identical masses and radii are rolling down an incline of given angle, and we know their initial height relative to the ground. An initial pass, this may seem like would be a conservation of energy problem with conservation of translational and rotational energy. However, it is not. And the reason for that is because of what we are asked to solve for. We are asked to find the initial velocity that the hoop would need in order to reach the bottom at the same time. And whenever you see the word time, you know that you're going to need Newton's laws, particularly Newton's second law, and you're going to need kinematics. And that's exactly what we're going to do in this problem. All right, so our first step is going to be use sum of torques and sum of forces on both objects to find the accelerations. All right, so we're going to use sum of forces and sum of torques on both objects to find their accelerations. After we have their accelerations, we then are going to use that information with kinematics to find an initial velocity for the hoop, which will have a slower acceleration, which stands to reason since it has a larger moment of inertia than the cylinder. But we will find that initial velocity for the hoop so that the times of traveling the distance are equal. So we're going to use kinematics to find v naught hoop so that travel times are equal. Okay, so let's get started with step one. All right, so with step one, we want to consider the sum of torques and forces. So to do that, we're going to choose a pivot for both objects at their center. All right, so here are both of their pivots shown in the figure. All right. And relative to those pivots, we're going to have a force that creates a torque, and that force is going to be the force of gravity. The force of friction. Because there is a force of gravity, but it acts at the center because we've chosen the pivot to be the center of mass, which I will label because that's going to come up later. So that's the center of mass of the hoop, and here's the center of mass of the cylinder. All right, and so then we have gravitational forces acting on both of them. Then we also have a friction force acting at the point of contact, like so. Okay, so this is Fg, this is F friction here, Fg, and F friction. Okay, so it's a little hard to see in that picture. I'm going to draw another version of it here. All right, so we can just kind of clearly see the what we have to consider for our setup. All right, so here we have our slope, and we're going to have our wheel on that slope, or just our circular object, right? Because they both have a shape that is circular, right? And then we have our center of mass. We've got our gravitational force vector, and then our friction vector. All right, those are the only forces acting on our objects. Okay, all right, and so then we want to then just think about the sum of torques relative and sum of forces relative to that pivot. I should say that is not; those aren't the only forces, right? You're probably wondering what about the normal force, right? So let's put that in there as well. Okay. Now it will turn out that the normal force, because it is parallel to the axis of rotation, or rather parallel to the position vector from the axis of rotation to its application point, it exerts no torque. But I'll mention that in a second. Okay. And here's our angle theta. All right, and then for completeness, I'm going to include the normal force vector here as well. Fn, Fn, okay. All right, so let's look at our sum of forces first, okay? So we have our sum of forces in x, our sum of forces in y, and then our sum of torques about the pivot. And we're going to have a tilted coordinate system, positive x that way, positive y this way, and we're going to define positive theta as the clockwise direction, okay? Okay, and and again, that's not a standard direction to apply positive theta, but there's no reason not to define it as that direction because that's the direction it's rolling. So you might as well have it moving in the positive direction. Okay. So then our sum of forces in x, we're going to have Fn minus a component of the gravitational force. So that's going to be Fg, but it's going to be cosine theta. Or sorry, I'm writing the forces for y, so let's put them in the right place. Fn minus Fg cosine theta, and that equals 0 because there's no acceleration in the y direction. All right, and we know it's cosine of theta because we can just think about the components of the gravitational force. All right, the two components here, and the angle. This is theta here. Okay, let's clean that up. So let's then think about the forces in the x direction. Well, we've got, oh, I miscalled it Fg, but I meant to, of course, label it F friction. So let's fix that. So that's the force of friction. And what that force looks like, or that's going to be in the negative direction. So our only positive facing force in the y direction is Fg sine theta. And we have the force of friction. And then that's going to equal ma com. So why do I write a com? Because I just want to call attention to the only translational acceleration that matters for the overall motion of the object is that of the center of mass. Because obviously there's different acceleration vectors at different points. Right? If we look at acceleration vectors in different points along the wheel, we're going to get different results. Right? Likewise on the cylinder, depending on what our acceleration is, we get different results. Right? We can look at different locations, but we only care about the acceleration of the center of mass, right? And that is a com. So it's basically the idea of taking the translational acceleration of the center of mass is that would be the translational acceleration of a particle that is behaving like our object. And obviously our object is not a particle, it's also rotation. It also has rotation, but its translation can be simplified to that of a particle as long as we look at its center of mass. It's one of the real utilities of the center of mass that's easily overlooked. Okay, so let's then, with that information, move on to our center of torques about our pivot. And obviously I'm not being specific about this for either the cylinder or the hoop at this point because we'll get to that. Okay, basically just solve for it with a general moment of inertia because that will be the only difference between them. Okay, so with the pivots, let's see. So with the pivot, we simply have the force of friction times the radius, which is defined as little r, times sine of 90 degrees, right? Because that's going to be the angle between the r vector and the actual application. So let's draw our r vector in here. All right, so right there, this is r. Okay, so what we see then is that, yep, sure enough, we have 90 degrees, and that's going to equal I alpha. And then the other two forces, the gravitational force and the normal force, both are 0 because the gravitational force is 0. So I'll say that tau g equals 0 because rg equals 0. And tau normal force equals 0 because theta equals 0. And sine of 0 is 0. All right, so we have two reasons why those forces don't create torques relative to our chosen pivot. Okay? So it's a good choice of a pivot then, right? All right, so let's move on to actually solve for that center of mass acceleration. All right, so I'm gonna do, so say using definition that the force of friction is mu k Fn, okay? And then we have mu k Fg cosine theta from the sum of forces in y, right, from this. And so then that's going to be mu k mg cosine theta is our friction force. Okay, so then we'll be well on our way to calculating our acceleration and so on. So what I want to take a look at here, though, and I noticed that there's a missing piece of information. I meant to define the friction coefficient here. So let me do that. Actually, never mind. I don't have to define the friction force. We could solve for it if we wanted to, but it's actually the friction force is implied by the very fact that these two objects are rolling without slipping. So there's a necessary friction force that's dependent on the angle and the shape of the objects. And so we could think of the object that's going to drive the friction force is going to be the hoop. And so we have to have a sufficiently large friction coefficient to actually have it not slip, because otherwise it would. But we don't need it to move on with our acceleration, so let's do that. Okay. So let's then substitute this information into our sum of forces. Okay, so we're going to go, sorry, our sum of torques. So then I'm going to go, so the sum of torques about the pivot is then going to be mu k mg cosine theta r. All right, sine of 90 is just 1. And then that's going to equal I, and then alpha is equal to A com over R. Okay. All right, and that's because of no slipping. Okay. Because of no slipping. All right, so if translation and rotation are synchronized, then that is always the case. So then we have A com divided by the radius of the object. Okay. So then let's go ahead and solve for A com then in terms of these quantities. Okay, so then A com is going to equal mu k mg cosine theta r squared divided by I. Okay, because I just multiplied both sides by r and then divided both sides by I. Okay, so then I'm going to substitute that into our sum of forces. Sum of forces in x. Alright, let's do it like this. Alright, so then I'm going to have mg sine theta minus mu k mg cosine theta is then going to equal, let's see, so I guess the usefulness of this is I'm solving for the friction coefficient. So let me see if I want to go a slightly different direction with this. Yeah, since I'm already doing it, I'm just gonna continue along this track, and this will allow me to solve for mu k, and then I'll plug it back in to eliminate it in my original expression for the center, or the translational acceleration of the center mass. All right, so mg cosine theta r squared all over I. Okay. Solve for mu k. And so then I'm going to have, right, so mu k times right? mg cosine theta plus m squared r squared g cosine theta divided by I. And that makes so much sense that we have an m squared r squared here in the I, because the I has that form of mr squared, which will then give us the same m. So, so our units work out. Okay, and then close parentheses there, and then that's going to equal mg sine theta. Okay, so then our friction coefficient is just mg sine theta. Let's make a big fraction out of this. All right, divided by mg cosine theta, which I factored out, and then that's I'm going to have 1 plus m r squared divided by I. Everything look good? Yes, yeah, I think so. Okay. All right, so then I'll factor that back in for mu k above. Okay, and so now substitute into a com above. Okay, so then that's going to give me that the acceleration of the center of mass is going to be mg sine theta divided by mg cosine theta 1 plus mr squared over I times mg cosine theta r squared. Alright, so these cancel. Alright, so then we're just going to get mg sine theta r squared over 1 plus mr squared over I, right? Which is a nice result, in terms of just being a general result for the acceleration of any shaped object rolling down an incline. Okay, so now let's do some shrinkage here of our font size and move on to solve to actually using that information in the context of kinematics to actually solve for part 2, which is the initial velocity of the hoop. All right. So let me just get this, move this up out of the way like so. All right. So part 2. All right. So taking a look at part 2, then we know that the hoop has a bigger moment of inertia, which means it's going to have a it should have a slower acceleration. And sure enough, we see here that as I increases, translational acceleration decreases, because we have, as this term goes up, this makes this term smaller. If we're dividing by a smaller number, then our acceleration is going to become larger. All right. Oh, hold on. Okay. Okay, so I see that I've left off an I in my calculation. So let's fix that. All right. So right here we should have had an I because it carried over from this one here. So when we factored in the replaced our coefficient of friction with this whole expression here, minus the I, right? Then the original mg cosine theta r squared over I should have been all there. All right, so let's fix that up. All right, so then this is multiplied by I So then our expression is going to become sine theta, or you could say really sine theta g. And look at g sine theta. So g sine theta, and then divided by 1 plus I over mr squared. All right, and obviously I factored in mr squared out of the denominator or the numerator and the denominator to get that result. But you can do the algebra for yourself to show that stat. But that's great. Now we got the translational acceleration at the center of mass. Okay. All right. So now, as promised, we're going to move on to kinematics. Okay. So let's think about it. So we need to think about the time to get to the bottom. So let's draw that distance. So this is going to be the distance we're interested in. Okay, well that distance is going to be, well, let's see. So opposite over adjacent, so sine of theta is h over d. So then d is going to be h over sine theta. Okay, and we have theta and h, so that's what we're going to work with. We're going to express d as h sine theta. So then we have two cases of kinematics. We're going to have, so I'm going to say using x equals x naught plus v naught t plus 1/2 a t squared. Okay. And desire for t hoop to equal t cylinder. Then we're going to have that our final position is going to be h divided by sine theta is going to equal 0, all right, plus some initial velocity for the hoop, so v naught h, right, times t, and then plus 1/2 times g sine theta over 1 plus mr squared over mr squared, because here the moment of inertia of the hoop is simply mr squared. All right, not going to be the same for the cylinder, because the cylinder is going to have 1/2 mr squared. Okay. So then, okay, and then we're obviously the cylinder is going to travel the same distance in the same amount of time. So let's think about it, because we have the same displacement, it's the same t, so really, so our t's will cancel, and we're just going to solve for v naught h. All right, so we'll set that equal, all right, because they travel the same distance. And this is going to be 0 plus 0 times t, because for the cylinder, it doesn't start with initial velocity. And then plus 1/2, oh, but I should add my t squared in here. So 1/2 a t squared, good, okay. And then g sine theta divided by 1 plus 1/2 mr squared divided by mr squared times t squared. Okay, so let me see if I can get that all to fit. There we go. All right, so let's think about this. So I mean, really, like I was saying, our only unknown is the initial velocity of the hoop. So what does this? Yeah, so we want to solve for that. We don't have the time other than knowing that it's equal for all of them. So So I would say the easiest way to do this is to find the time that it takes the cylinder to travel to the bottom, and then plug that into the displacement equation for the hoop to solve for the initial velocity of the hoop. Okay, so it's because the desire is for it to be the same time. So I'm going to have the time. All right, so I'll say from cylinder. We can cancel this term out here. So we so we're going to end up with h over sine theta is going to equal 1/2 g sine theta over 1 plus 1/2, so 3/2. Okay, and that's times t squared. Okay, so let's see. So 2/3. Okay, so then that becomes h over sine theta equals 1/2 times 2/3 g sine theta t squared. Okay, our 2's cancel. Alright, so then our time, okay, so we're going to multiply both sides by 3, so we're going to have 3h, and then divided by g sine theta squared, so g sine theta squared, and then that's going to be inside the square root. Okay. So then we can rewrite that as, so, I mean, we have, obviously it's sine squared, so it's going to come out of the square root, so it'll be 1 over sine theta. Times 3h over g. Okay, and so then if I then move back, so say returning to the cylinder, or returning to hoop, or substituting into hoop equation. What we're going to get is h sine theta v naught h, okay, 1 over sine theta square root of 3h over g, right, and then plus 1/2 g sine theta. Alright, because we have cancellation here, where we just have g sine theta over 1 in the case of the hoop, and then times the time that we desire squared. That's the time that it takes the cylinder to get to the bottom. So 1 sine squared theta, 3h over g. Okay, so now we are ready to solve. Let's go ahead and see how we can simplify this. Let's see, so we have in terms of thetas, right, so this one's going to cancel with this one, which means we have a 1 over sine theta in every one of our terms. Okay, so they completely cancel out, so the angle completely cancels out, because it's going to be true of any angle. It shouldn't be dependent on the angle. It should be only dependent on the shape and the amount, basically the distance, which is represented with h here. That makes sense, I suppose. Okay. Right, looks good. And then we want then to think about how we're going to express this. Okay, so we have 3h over g. Oh, g's cancel in this term as well. So we have 3/2 g and an h. So I'm going to be subtracting 3/2 g from both sides. right? So V naught hoop is then going to be -1/2. Well, let's write it this way. Sorry. So V naught h times the square root of 3h over g is an equal -3 halves h. The issue here is that we're going to end up with a negative value. So I wanted to check my signs here real fast. All right, so I made a slip up here on my arithmetic. So we still have g sine theta in the top, but we wouldn't have 1 in the denominator here. We'd have 2. So the idea here is I pointed out that for the hoop, we have mr squared over mr squared, but that's 1 plus 1, which becomes 2, whereas here we had 1 plus 1/2, which became 3 halves, which of course showed up here. So we have an expression of 2, which is our 1/4, which is why we will not end up with a negative value. So let's fix that. All right, so we're going to have 1/4 here. Okay, so 3/4. So we have h minus 3/4 or 1/4 h over g. Okay. Oh, and we still have all our cancellation of our g sine thetas. Yep, absolutely. Looks good. All right. Good. And we'll see that not all of our g's will cancel, but these ones do. In this expression here, this g cancel. All right. So moving on. So again, we have an h over here, and then we have an expression here, which is 3/4 h. Right, so there's our quarter, there's our 3. So we have h minus 3/4 h. All right, so we have a 1/4 h value there. So we are nearly done. Let's just squeeze in our final calculation. Right? And definitely a testament to keeping everything symbolic. We're really able to show a very simple result, right? Because if we just kept doing numbers, we wouldn't see how everything is connected, which is fine. You still get the answer, but it is interesting. Okay, so then we're just going to multiply, and so we're going to end up with 1/4 h divided by the square root of 3h over g. So if we're dividing h by the square root of h, we're going to end up with h in the top of the square root. We're also going to have g up there. And then we're going to have square root of 3 in the denominator. And then a 1/4 in front. So look at this. Okay. Let me just check units wise, right? So we have meters per second squared for our acceleration, meters. So we end up with meters squared per second squared, which, okay, that'll work. And then we could bring the 4 inside the square root, which becomes 16. So it just becomes 16 times 3. But either way, we are ready to plug in our values. All right, and just checking everything. Okay, yep, it all checks out. Okay. All right, so let's finally find our velocity, which is dependent on basically just the height and the planet that this takes place on. Right, so it's going to be the slope only matters in as much as it's going to make, if for like a fixed distance, if you change the slope, then, for a fixed size ramp, if you change the slope, then obviously it would change the height. But really it just depends, how much potential energy, in a sense, it has. Although we can't do this with energy, again, because it is a time question. We have to do it with accelerations and kinematics. Okay, so we'll have let's put our 0.25 in the front. That's our 1/4. Then the square root. All right. And then our height which is given as 2.4 meters. All right, so 2.4, and then multiplied by 9.8, divided by 3. All right, so we have an initial required velocity of 0.7 meters per second. Pretty cool. All right, wow. All right, well, thank you for listening to this interesting problem.